Hello everybody, this is Dr. Christopher White and welcome back for part 3 of our video series dealing with the lab exercise Modelling Precambrian Surface Conditions. So we've now moved on to part 2 of the lab exercise. So for question 1 of part 2 we're going to start looking at Venus. So the information that you're going to need for the surface temperature calculator is given in this block of text right here. So let's begin by looking at Venus's present day conditions. So for the surface temperature calculator, you're going to still use a solar mass of 1, and your distance to Sun is going to be set at 72% of the Earth. So we know that 1 AU is the distance between the Sun and the Earth. So obviously if Venus is located 72% of that distance, then it's going to be 0.72 AU. So you're going to be putting 0.72 into the surface temperature calculator. The bond albedo for Venus is 0.77, which is equivalent to 77%. Remember, we are working on a scale from 0 to 100 in the surface temperature calculator, so it is 77 that you want to put in the calculator, not 0.77. And the greenhouse effect is 200, because as we know, Venus has an extremely strong greenhouse effect due to its very thick carbon dioxide rich atmosphere. Okay, so once you've inputted all this information into the surface temperature calculator, it's going to give you the current surface temperature in Fahrenheit and in Celsius. So not really that surprising, the number you're going to get is going to be pretty high. So for question 2, it asks you to look at the metals which are listed in the table on page 2. So if we go all the way back up here, you will see there are 5 metals given: aluminium, iron, lead, silicon, and titanium. Although technically silicon is a semi-metal. So what you're going to do is you're going to look at these 5 metals and you're going to say, right, based on the temperature that I calculated, which one of these metals or which ones of the metals will melt on the surface of Venus. Now, please remember that the melting points that are given are in Celsius. So please don't look at the temperature in Fahrenheit and then try and, use the melting points in Celsius. No, you have to use the surface temperature for Venus in Celsius and compare it to the melting points in Celsius. All right, so once you've done that, you are going to list the metal or metals in the space here. So for question 3, we are going to be thinking about the early life of Venus. So as we've already discussed, in the early solar system, we know that the sun will have been less luminous, 20 to 30%. And so this means that Venus will also have experienced a faint young sun paradox. So even though there's no evidence for it anymore, we believe based on modelling that during this time period, Venus, like Earth, would probably have had liquid water on its surface. So we're going to think about how it managed to overcome the faint young sun paradox and not turn into an ice cube. So how are we going to do that? Well, we're going to begin by obviously working out what values we're going to put into the surface calculator. Now, to begin with, we know obviously the mass in solar masses of our star is going to be 1. So that one's relatively straightforward. Next, we need to start thinking about the amount of energy that Venus is receiving. So we know that Venus was receiving somewhere between 20 and 30% less energy from the sun during this period. So how are we going to account for that? Well, what we're going to do is we're going to move Venus 20 to 30% further away from the sun, thereby reducing the amount of solar radiation it would receive relative to the modern day sun. So what we'll do is we will increase the distance between Venus and Sun by 25%. And so what you need to do is you need to take the distance value for Venus as it is now and increase it by an additional 25%. So an example is given to you here. So if you imagine that our planet is 2 AU away from the Sun, and we need to reduce the amount of solar energy it receives by 30%. What we would do is we would take our distance, 2 AU, and we would multiply it by 1.3. So that's essentially 130%. And that would give you a distance of 2.6 AU. So by moving it that little bit further away from the sun, you help to reduce the amount of solar radiation the planet receives, and thereby you bring the temperature down. So it's more, it's more realistic for the amount of solar energy that Venus would have been receiving during this faint young sun paradox phase. Okay, so we've now worked out how you are going to calculate the distance. The next thing we need to work out is what's the bond albedo. Well, this one is particularly complicated because we don't actually know, how much of the surface of Venus was covered in water. Was it a small amount? Was it a large amount? And so that makes estimating the bond albedo somewhat tricky. However, the best fit that we can probably use is to look at other planets that have a similar crustal makeup to Venus. So we know that the surface of Venus is predominantly covered in basalt, and we also know that the surface of Mars is also predominantly covered in basalt. So what we're going to do is we're going to use the surface of Mars as a guide to estimate the bond albedo for Venus during this time period. So if you go and use this hyperlink right here, it's going to take you to a fact sheet for Earth and Mars. And as part of that fact sheet, it's going to give you the bond albedo for both planets. So what you need to do is you need to find the bond albedo for Mars. And this is the important part. You need to convert it to a percentage. So in the data sheet itself, it's going to give you a bond albedo value, let's say, of 0.77. All right. That is 77%. So it's the 77 that you will put into the surface temperature calculator. Or if it was to give you a bond albedo of 0.1, that's equivalent to 10%. So you would put 10 into the surface temperature calculator. All right. So now we've done mass, we've done distance, we've done bond albedo. The final variable is the greenhouse effect. So this one is also pretty difficult to estimate because we can't be 100% sure what Venus's early atmosphere was like. However, we can assume that based on Venus being a relatively similar size to Earth and having a very, very similar bulk composition, we can assume that the atmosphere at that time was probably quite similar to that of the Earth. So, excuse me, what we're going to do is we are going to be conservative in our greenhouse effect, and we're going to say that it was 50% stronger than present day. So obviously we know that the present day greenhouse effect has a value of 1. So in order to make it 50% stronger, you obviously need to take that and multiply it by 150%, because you need that extra 50. So you would do 1 multiplied by 1.5. Okay. So once you have that information, you are going to put the values that you calculate into the free empty spaces here for distance, bond albedo, and greenhouse effect. So now you've done that, what's next? Well, obviously you're going to put them into the surface temperature calculator, and you are going to calculate a temperature for the surface of Venus during this faint young sun paradox time period. And I need to be clear, because the greenhouse effect is so low, this is going to be quite a conservative estimate. It could have been considerably hotter, or in theory, considerably colder. So once you've done that, that's the end of part 2. So for part 3, we are also going to move on and look at Mars. So once again, for question 1 of part 3, you have been given information about the conditions on Mars in the present day. So solar mass of 1, distance to the sun is 152% that of the Earth's, so 1.52 AU, that's the number you're going to put into the calculator. Bond albedo is 0.25. So you're going to put 25 into the calculator. And the greenhouse effect is 0.1 because the atmosphere of Mars at the moment is so thin and tenuous that it barely has any greenhouse effect at all. So you are going to take this information, put it in the surface temperature calculator, and it's obviously going to give you the temperature in Fahrenheit and in Celsius. So for question 2, we are going to be doing exactly what we just did for Venus. We're going to be thinking about what the conditions would have been like during this faint young sun paradox phase. Now, obviously, we know Mars is even further away from the sun, So we know the faint young sun paradox would have had an even greater effect on the surface temperature of Mars, and it would have want to have made it, much, much colder than it is, at present. Although, to be fair, at the moment, it's still pretty darn cold. So what are the conditions for Mars during this faint young sun paradox phase? So we're going to repeat the same process we used for Venus. So for the distance, we're going to move it 25% further away from the sun versus the present day. So the present day value is 1.52 AU. You're going to increase that by 25%, and that's going to give you your new distance. Bond albedo, go and look at that NASA data sheet. It actually just tells you the bond albedo for Mars. Use that. Greenhouse effect. Well, we are going to assume that Mars at that time, just like Venus and Earth, had relatively similar atmospheres, and so we are going to be using the same greenhouse effect that you just calculated for Venus. So up here in question 3 for part 2, you are going to have a greenhouse effect that you calculated for Venus. You are going to use the same value, and you're going to drop it into the table down here for Mars. So once you've done that, you are then going to put those values into the surface temperature calculator, and you're going to get the temperature in Fahrenheit and in Celsius. And then once you've done that, you are going to move on to question 4. So what you're going to realize when you do your calculation for question 3 is that it's cold. However, we know that the early surface of Mars did have liquid water. And so once again, we have one of these issues where the calculations are showing that one thing should be occurring, but the geologic evidence is telling us something completely different. And so this obviously tells us that, right, the greenhouse effect must have been a lot stronger than the greenhouse effect we have just modeled in our surface temperature calculation. So what are you going to do? So you're going to keep these values the same. So you're going to keep your star mass at 1. You're going to keep your distance at whatever you calculated. You're going to keep your bond albedo at whatever you calculated. And the thing you're going to be varying is the greenhouse effect. And so what you're going to do is you're going to start at a greenhouse effect of 1. You're going to see what the temperature it calculates is. Then you're going to move to 2, 3, 4, 5, etc. until you eventually get to a point where you take the surface temperature of Mars above 0 degrees Celsius. So liquid water would be able to exist on the surface at that time. And that's going to show you how much stronger the greenhouse effect on Mars would have had to have been in order to produce the liquid water on the surface that the geologic evidence is telling us was there. Okay, so that's it for this video. Thank you for watching and have a good day.